Hi guys, welcome back to the channel. In this video we are going to discuss about D flip-flop. In the previous video we have already covered about SR flip-flop. So this is very simple than SR flip-flop. So let's get started. Before seeing the D flip-flop, let us have a quick overview of SR flip-flop. So if you see, the SR means S means set, R means reset. So we can simply say set reset flip-flop, we can simply say. So this is the block diagram and this is the truth table for the SR flip-flop. And one more important thing, there is concept called the conversions. So we can convert SR flip-flop to D flip-flop. So as with the help of a single NOT gate. So you can see over there we are passing clock directly and we are passing an input D to S and D bar to the R. So this is known as D flip-flop. So we can implement the D flip-flop with the S flip-flop. So this is known as conversions. So conversions in a simplified manner will be covered in the upcoming videos. But about only D flip-flop we are going to talk in this video. But what is the main issue in the SR flip-flop? The main issue in the SR flip-flop is when you pass the both S and R as 1 then the output would contain as forbidden state. So for the avoiding of that state we are going to use D flip-flop, JK flip-flop, this kind of flip-flops we are going to use. So let us understand D flip-flop here. So if you observe, D means here called delay. So the name itself suggests that delay means as you're sending input it delays and again the same thing will be returned in the output. So if you see here, this is the block diagram of the delay flip-flop. There is only one input called D and two outputs Q bar, and we have clock over there, that is as usual. So this is the block diagram. So this is the truth table of the D flip-flop. If you observe clearly, so clock is when high only the whole things will be working, that is already we know. So when D is 0, so there you can see two outputs, means one is QPS means present state, another output is QNS means the next state. We can also call them PS as the QN only and the next state as QN plus 1, simple representations that I am representing there. So present state as QN, next state as QN plus 1. So this flip-flop is generally designed to as simply make delay and produce the output. So if you consider, I have highlighted two columns, that is D column and the next state column, because both of them are means the same. So whatever may be the input you pass, the same input will be produced that output. So whatever may be the thing that present in the present state, that doesn't matters. The thing that you are passing, the output, the next state output that you will be obtaining in the output. So if you pass 0 in the D, you will get output as 0. So that is the thing that I am saying. So D and Qn plus 1 are same. So this is the important point, remember this point. So now let us also understand the delay in the delay flip-flop, the clock transitions. So this also works based on the clock rising and falling edges. So we are going to pass the clock signal in that clock. So first let us understand the positive edge triggering. So in the positive edge triggering, we can simply show the block diagrams the same. So there is no change in the clock, all the things would be same in the block diagram. So if you see, we have clock and D as inputs. So I took clock according to the positive edge triggering, we have a rising edge. So I took another input D, a random thing that I have took. So now we are going to produce the output Q according to the comparison between clock and D. So if you compare the first rising edge and the input D, so that is rising, means the highest high level. So we are going to have high level up to the next rising edge. So in the next rising edge, if you see, compare the clock and D. So my clock is rising edge, D is what? The D is low. So there we need to make clock means output transition from 1 to 0. That is the thing that we are going to see. Because clock is rising but D is again low, we are going to have the clock transition Q as low. In the next rising clock edge, you can see over there that the D input is again high. So we need to make our output Q as high again. So we have obtained the timing diagram of Q output Q, but we have another output called Q bar. So we can simply obtain the Q bar by simply reversing that with the Q. So when high Q is 1, Q bar would be 0. So this is a simple. So next we are going to see with this is negative edge triggering. So if you see the block diagram over there, top right corner. So I have changed the block diagram. I have added a bubble with the before the clock. So before the triangle I have added a bubble. So this bubble is very important for the representation of the negative edge triggering. So if you also see, according to the negative edge triggering, I have changed the clock pulse also. So but input I take that D as same. So the first falling edge, if you compare D and clock edge, so that is rising only. So you are going to up to the next falling edge, you are going to follow the up high level only. The next falling edge, if you compare with D is low. So low, according to that, we are going to change our Q output also, the timing diagram of Q. We have to make Q as low there. You can see over there. And finally, if you observe the last falling edge that is corresponding with D is rising over there. D means high over there. So again in the output you are going to make change as high over there. So in the same fashion, if you want Q bar, so the same thing we are going to see, because this is also another input of the negative edge triggering D flip flop. So simply invert the Q, you are going to have the Q bar. And we have called something called different representations of flip flop. So we have truth tables, characteristic equation, excitation table, state transition diagrams. So I hope you know about truth tables. This is very basic thing. So the another one called characteristic equation, excitation table will be discussed here only. But the about state transition diagram is a very important concept in the sequential circuits. So this thing will be discussed in a separate video. But let's see these two things today. At first, we are going to understand what is meant by characteristic equation and the characteristic table. So characteristic table means the normal table that we are seeing here. So this table is known as characteristic table. So in the combination circuits, we are going to call it as the truth table, but here we are going to call as other names it as well. So characteristic table. So we are going to have the characteristic equation. So characteristic equation means the general equation of every, means the relation between output, means the next output, and the input, present input. So that is known as the characteristic equation. So if you see, we can have a simple relation in the D flip flop. So we might have some complex relations in the JK flip flop or S flip flop, but in the characteristic equation of D flip flop, it is very easy. That is, so Qn plus 1 is equals to D. We have simple relation because the name itself says that is delay flip flop. Delay flip flop means it produces delay. That's it. It doesn't make any changes. So in this flip flop, whatever you pass will be presented as the next state output. So we can have simple output expression in terms of input. That is Qn plus is Qn plus n is equals to D. So this is known as characteristic equation. So whatever may be the input you are sending, so if any output is present over there, present output, kick it off and present new output as D itself. That is known as Qn plus 1. Because that is the reason Qn plus 1 and D are same in this delay flip flop. So in this excitation table, it is nothing but the exactly same of truth table only. But you are going to represent in the reverse format. First you are going to represent outputs, then you are going to represent the inputs. So why this came into picture? Because these tables are very much useful in the flip-flop conversions. At the starting of this video, I have mentioned that we can perform so D flip-flop with the help of SR flip-flop. So how I made that? Because with the help of the some logic, right? So that logic can be built with the help of the flip-flop conversions and the excitation table. So these things will be clearly explained in the other videos. But just for this video, just remember or know about excitation table means we are going to represent output input as a table from opposite way. These are useful in flip-flop conversions. Remember up to this for this. So in the previous video we have covered about gated SR latch. I hope you know this. So this is the basic SR latch with the enable line and two inputs S and R. Output as Q and Q bar. Now we are going to convert this gated SR latch to the D flip flop. How to do that? Let's see. So for the conversion of gated SR latch to the D flip flop, first of all we need to convert gated SR latch to the gate D latch. So see this clearly. This is gated D latch. How we converted? Just add NOT gate over there in the R input and just convert the down input as D as a single input. So this is known as gated D latch. So already we have know that if you have any gated latches, we can simply convert into flip-flops. How? So in the place of enable, you have to place a simple circuit called clock transition circuit. With the help of that circuit, simple circuit, the whole circuit becomes a flip-flop. So that is the flip-flop I am saying, right? So this whole circuit is known as D flip-flop. So I have done nothing new. For the D latch, I have just added the clock transition diagram, means the circuit in the place of enable. That becomes our whole D flip-flop. So the same things is elaborately, detailedly discussed in the SR flip-flop. So check it, SR flip-flop, SR latches in that videos. So I am giving that videos in the description box, check it out. So in the SR latch, we have detailedly discussed what is there inside the box, but we need to also discuss what is there inside the box of D flip-flop. So this is the thing that is present inside that D flip-flop. You can see over there, we have some clock and we have some input D. So the same thing present inside the whole box, but simply we are representing with the help of the block diagram. We have clock and D and two outputs Q and Q bar. I hope you understood about the D flip flop. In the upcoming video, we are also going to cover JK flip flop and T flip flop. So stay tuned. Thanks for watching up to now.